Section 4.9 is all about solving a quadratic equation and using the factors to do so. This is not the only way to solve a quadratic equation, of course, but it's one way, and it's a kind of step into solving quadratics. And remember that in section 4.8, we multiplied polynomials to create more polynomials, and in particular now we're going to be looking at multiplying linear polynomials, and those will be our factors. If we have two linear polynomials and we multiply them, we will end up with a quadratic function. Okay? We will also look at the x and y intercepts of images of quadratics, of parabolas, and then we will actually get to the nitty-gritty of solving quadratic functions using their factors and graphs. So, I'd like you to recall that when we were multiplying these factors, we needed to remember to multiply all terms from the first set of parentheses times all terms in the second set of parentheses. So, remember to multiply all terms from the first set of parentheses by all terms in the second set. Yeah. Okay. And then I also wanted to, this is more of a remark than it is a recall, but when the factoring, so now we're going to talk about these factors. The factors were what was in these parentheses that we were multiplying, and factoring is the undoing of distribution so that we have two things being multiplied. So factoring is the undoing of distributing or multiplying. Distributing. Okay. We literally multiply factors. I mean, they're called factors. This is a factor and that is a factor. We multiply two factors and we get the product. Okay, so that is our jargon, just how we name things. And we will use it. We will use these factors and to find out where they will be equal to some values. So, just going to write this down, and then, so factoring is the undoing of distributing. Let's multiply and graph. Okay, the first one says check to see if the term x minus 4 times the factor x minus 4 times the factor 2x plus 3 is equal to the general form of this quadratic, 2x squared plus x minus 12. Let's see if that's true. Okay, ready to rock. So, x minus 4 by 2x plus 3. And notice each one of these factors is a line in its own right. Yes, this is a linear factor, and this is a linear factor, and now we are distributing it. Here we go. So I see an x by 2x, so that would be an x by x makes an x squared. So this is 2x squared. X 3 times, so 3 x's, or 3 x 3 times is the same as 3 times x. And let's see, we have 4 sets of 2x's, but the opposite, so I put in my opposite here. 4 sets of 2 is 8, so 4 sets of 2x's is 8x's. And also we have 4 sets of 3 and the opposite of that, minus 12. So these are squares, and those are not like non-squares here. We have 3 x's, take away 8 x's, so we actually have negative 5 x's. Uh-oh. So, nope. This does not equal that. Excuse me. Right here and right here. Not equal. They are not the same. They are not equal. So take a peek here, take a peek here. No. Okay, now it's been modified. So this quadratic, this general form of a quadratic has been modified to 2x squared minus 5x is minus 12. Let's work it out. Okay. The factor x minus 4 times the factor 2x plus 3. Okay, I see x by 2x, and an x by x is an x squared, so there's 2 of them. And I see x by 3, which is the same as 3 by x. And I see 4 sets of 2x, opposite style. Okay, we've done this before. Same as up here. And that is 2x squared minus 5x minus 12, which we just saw. And notice, yes, equal. So these truly are equal. These are not. Graph the factored form and graph the general form of these quadratics. Okay, here we go. Now, when we start graphing, immediately I think that we're going to need some pieces of this, and we're going to use our graphing calculator too. So if these are quadratics, then it's really important to know where the vertex is. Well, x is equal to the opposite of b over 2a if it is in the general form of the quadratic. So I look at this is factored form. I look at this is general form, and that's our go-to. So I notice here's a is 2, b is negative 5, c is negative 12. As a matter of fact, let's write that. And all of that information was much easier to get from this form of it than from the factored form of it. Okay, so the opposite of b is 5, and double the a is 4. And so x, the vertex happens when, okay, that goes into it one time, at 1 1/4. And then we would need to plug this in to the x value in order to get the y value. But since we're going to do this a lot, I'm actually going to make a table of values here. So, and we're claiming in number 2 that they're equal. We're about ready to see. You know what? I will use purple for the factored form. And I'll go over here and I will use blue for the general form. Okay. Right. I'm going to go ahead and work. Okay. There's a glare. Y equals, okay, the quantity x minus 4, you know what, I'll go, what is it, 2x squared minus 5x's minus 12. Let's graph this. Okay, so I see at that 1 1/4 there's the axis of symmetry, and it peaks somewhere down here. But I'm going to have to zoom out. So let's go ahead and do that quick. All right, so there it is, 1.5 down there. And I also would like to have a table of values. Oh boy. So let's see. I know that it happens at 1.25. So I see that we have some whole number coordinate pairs here, which is great. But I need to know what happens at 1.25. So see this table set right by window. We're going to need to go second table set. I don't know. Let's start it at -2. Hopefully that's enough. But I'm going to have to go by quarters. Okay, so now I'm going to go back to second graph in order to see the table. And it has started counting by quarters. I see at -2 at 6, -1.5 at 0. It looks like I'm actually maybe thinking about making my X scale by halves, because those seem to be pretty decent points on my graph. And then I'll use my Y values from this T-chart. Okay, so let's see. I see -2, 6, -1.5, 0, -1, -5, 0, -12. Okay, a half and -14. Okay, 1 is at -15. But remember, 1.25 at 1.25. Oh my goodness, I'm so sorry. There we go. But remember, our vertex happened at 1.25. So I'm going to have to put in 1.25. Nearing the center of my chart here. There's a lot of data here, and the calculator approximated this to -15.13 or 15 1300ths about. And then at 1.5, -15. So just to give some symmetry here, and notice here's the vertex, right? So here's the vertex, the center of our image. And then around it, we're seeing this symmetry happen. 2, I bet 2.5 is -12. And then it bounces back. Yep. Okay, so, we have some decisions about our scaling. It looks like we dip into the negatives quite a bit. And our X values are, I mean, they're small. They don't vary very much. So I think the decision I'm going to make is perhaps it would be fitting to make sure I have a little bit more negatives in the Y's. So I'm going to move my scale, my X axis up a little bit so that I have more below it. My Y scale, I have X's on both sides, but I guess I could move it over maybe 1 or 2. Okay, so I'll move that one over 2 as well, just to give the positives a little more space here than the negatives. And let's see, okay, in my X's, they're close together, so I'm going to go 1, 2, 3, 4. And to the left 1, to the left 2. Okay, so that would be my -2 right there. And on my y-axis, I'm going to count by 2s because I have to get to -15.13. So I think 2, 4, 6, 8, -10, or 10 below. 2, 4, 6, 8. Okay, that would put us at -18 at the very bottom of this grid. Okay. And then above it, 2, 4, 6, 8. Okay, so this would be 8 above. Okay, so I did have to rescale just to work this out. Okay, let's plot these points. All right, general form. It was -2, 6. 2, 4, 6. Got it. -1.5, 0. Check. -1, -5. 2, 4, 5. Got it. 0, -12. A half and -14. So right here. Okay. Whoa. That is not where I was supposed to be. At a half, it's -14 at a half. 10, 12. Okay. Whoops. I do not want to be confused by my mix-up. Okay. There. And then let's see. At 1, it's at -15. 1, 2, 4, 5. Got it. And at 1 1/4, it's our peak. So if this is 1, and and we're counting by halves, something of the sort right there. And then at 1 1/2, so 1 1/2, we're at -15 again. Okay, at 2, -14, -10, 14. And at 2.5, 1, 2, 2 1/2, -12. So here's -10, -12. Got it. And let's see if we can work with this on the symmetry front here. Let's see. So we have this one symmetrically, and then this one. So that was -1, -5. Okay. And then, let's see, that one's symmetrically. Here's our, I'm actually going to draw in the axis of symmetry here. Okay. How far away is it? So it is 1, 2, 2 1/2, 2, 2 3/4. So here's 3/4, 1, 2, right there. Okay, I think that this one actually was supposed to be right here. I think I messed that one up. Okay. There's our parabola. Yay! We also could plot this point by symmetry. Half away from that is +6, 2, 4, 6. Okay, so symmetry is actually quite powerful. Reduces our computation. Okay, that's a pretty, I mean, that's a lot of points, and that looks like a pretty solid parabola. Got it. Now let's do it for this one. Yes? Okay, so I'm going to go back to my graphing calculator. I'm going to go to y equals, clear this, and put in x minus 4 times the quantity 2x plus 3. Enter, and graph. Huh, that looks familiar. And table. Huh, that looks familiar. So notice that these table values are identical, right, to these table values that we did for the last graph, where it was in its general form. But now it's in its factored form, and we have the same table of values. And that's because we said that they were equal. Okay, so in terms of the table of values here, it is exactly the same. Same. I copied the table of values. It's exactly the same. Okay, so I'm going to graph this and I'm going to make the same decisions. I mean, the same decisions that I made before, I'm going to make again. So these are scaled. They're pretty small, so I can spread them out. But these are pretty negative, so I'm going to move my x-axis up a little bit. Done. And, okay, these are, it seems like there are more positives than negatives in order to balance out the symmetry. So, okay, I'm going to move this over in order to give us more positive x's in terms of what we're seeing. And let's see, these are more spread out. So I go 1, 2, 3, 4, and 1 to the left, 2 to the left. Got it. And 2, 4, 6, that's 6 above. And whatever, that's 8 right above it. And 2, 4, 6, 8, 10 below. 2, 4, 6, 8, so that's 18 below. Got it. I'm noticing that this is very similar. My actions are incredibly matchy-matchy here. Okay. Got it. Check. 1 to the left, 5 down. 2, 4, 5. Check. Let's go to the vertex. So 1.25 and 2, 4, 6, 8, 10, 12, 14. Uh-oh, I just lost track, sorry. 2, 4, 6, 8, 10, 12, 14, 15, and a little. And at 1, it was 15. 2, that's 10, 12, 14, 15 below. Got it. And then at 2 and at 1/2, it was negative 14, the output, or the y value. So at 2, 1, 2, here's negative 10, 12, 14, and at 1/2, here's 1/2. Got it. 2.5, 1, 2, 2.5, here's negative 12, no, that's negative 10, here's negative 12, and where was that over here? 0, 10, 12, done. And then we started using symmetry. I'm remembering this very well. Okay, so even though I'm not including all of the points that I included on the other one, I'm including these. And voila. Okay, so when two things multiply and they are equal to each other, then their graphs, their images, are going to look identical. If you scale them the same and you have the same window, their tables are definitely going to look exactly the same. And, I mean, everything, so here's the axis of symmetry, right, through the vertex. So there's a lot that can be said about this. For instance, they have the same vertex, they have the same axis of symmetry, they are equal to each other, their images are the same. For every x value over here, it has a y output. For every x value over here, it has the same y output that this one did. So even though they don't look the same, this is in factored form, and this one is in general form, they still have the same performance. So you can take two ways to get to Chicago, but you're still going to Chicago. Or, you know, so the way you get there might look different, but the fact that you got there is the same. So, but there are, I would like to mention a few things. Like I noticed that this one hits the x-axis at 4, and I noticed that a 4 appears in this factored form. I noticed that this vertex with the formula, of the opposite of b over double the a is so much easier to find from this form, the general form, than it was from here because I couldn't really see those in this point of view. It was much easier to find a table of values to compute in the general form, so that's a thing. But I also know that when we do this, so another thing that just happened is that if we multiply, what was it, 2x squared minus 5x's minus 12, when we multiply and we come up with a solution, that when we graph both of them simultaneously, right, they are the same image. And that's pretty significant. For instance, in the first one, it was asking, is this equal to 2x squared? 2x, oh, really? 2x squared plus x minus 12. And I go to that graph. So they are not the same. So when we are able to say something like, check to see if these two linear factors multiplied equal this quadratic, well, either you can multiply this out and see that they they made a mistake here, something happened, or you could go to your graph and say, well, they're not, every time you put in an input, they do not have the same y value output, so they are not equal to each other. One gives you more or less than the other. Okay, so now it's saying this has been done correctly, verify. We are going to verify in two ways, yes? We're going to verify it by distributing, because we definitely need to remember how to do that. So let's do that quick. Okay, so x plus 7, that line, times the factor x minus 3, that line, is equal to x by x is x squared. X 3 times, but the opposite, so negative 3x's, positive 7x's, and 7 sets of 3 is 21, but it's negative, or the opposite, which is, okay, let's see, negative 3x's plus 7x's makes 4x's, which is exactly what we see here. So yes, so that means that they should have the same graphs. Let's make sure that happens. Okay, again, I'm going to start with the vertex. The vertex has x equals, I look at this, I don't see ABC. I look at this, I see ABC. Sadly though, the A is a silent 1 because when they only write an x squared, they really imply that there are 1 x squareds. There are 4 x's and negative 21 regular units. Okay. Let's see, more or less, I guess. Opposite of b is negative 4 over double the a is 2. That is negative 2. Wow, that was really tricky to write. It looks like a congruence. Anyway, it's negative 2, and the y value that goes with that, let's see, negative 2 by negative 2 is 4. 4 minus 8 minus 21. Whoa. 4 minus 8 minus 21. Negative 25? Wow. Okay. So I see that our y values are going to get all the way down to negative 25. And our x values are going to be surrounded by the mirror image happens around negative 2. So immediately I know that we're going to need to move our y-axis over to the right because we're going to have more negative x's, and we're going to need to move our x-axis up because we're going to need more negative y values as well. Okay, let's do that. Negative 25 is pretty far down there. Negative 2 is like, it's close. Right, so now I'm going to go ahead and I'm going to clear these out, but I'm going to use my calculator to create my table of values. X squared plus 4x's minus 12, and I think we're going to need to change our scale. Like, we don't need to count by quarters in this one, I don't think. So let's go to second table set. I don't know if we want to start. No, we don't want it to start at -2 because that's actually the vertex. So let's start it at -5 perhaps. Count by ones. Okay, I see. Did I miscalculate? How did I miscalculate? Okay, hold on. It's telling me that I have made a mistake. 2 squared, +4. So -2 squared is 4. 4 minus 8. Oops. I see. I computed by hand correctly, but when I put it into the calculator, I put 12 instead of 21. Okay, table. Good thing I did a calculation by hand. Jeez. Okay, so let's go ahead and make our table for this. -2 at the center. Okay, so here's -2 at the center. And let's go around it, yeah? So -2, -25, -1. That's actually bigger than it. So let's go -3 below it, -4 is below it, 0 is above it. Okay, so I just picked things surrounding our vertex on either side. If we go -4 style, that is -21 as a y. -3 is -24. And, okay, well, geez, I'm going to want more. If we plug in 1, we get -16. If we plug in 2, we get -9. And if we plug in 3, we finally get 0. Yeah, I needed more values because I saw that this was all very close together and all negative, so I put in some more. Let's graph. -4. If I count by 2s, is this going to make it? So I know that my x values will make it, wait, 1, 2, I can count. That's 3. 3, 0. And -1 to the left, 2 to the left, 3 to the left, 4 to the left. Got it. And going down, 2, 4, 6, 8, 10. Yeah, this is going to work out. Okay. 2, 4, 6, 8, 10 below. 12, 14, 16, 18, 20 below. 22, 24, 26. That's 26 below. Okay, I'm ready to plot. -4 and 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21. Okay. -3. So 3 to the left, 24 down. 3 to the left, and that was 21, 22, 24. Got it. 2 to the left, 25 down. So 2 to the left. This was 24, 25. That's our peak. Got it. Okay, and then let's see. I'm at -1, -24. So here's -20, 2, 4. Done. 0, -21. Got it. 1, negative 16. So here's 10, 12, 14, 16. 2, negative 9. 2, and here's negative 10, so just above that, and 3, 0. Got it. Okay, so I've plotted all of these points, but I'm noticing I could probably include this symmetric point over here. So over here, let's see, yeah, so there's its symmetrical point across. Here's the axis of symmetry and the vertex. And then let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, it would be somewhere over here. Okay, so here we go. Let's make our parabola. Rough sketch. Opening wide but symmetrical. Okay, now let's do the same thing, but for the factored form. So we're going to make our T-chart. Go back over here and go to y equals. I'm going to, oh, by the way, did we graph this? There you go. Yeah? So ours looks a little bit wider just because we took this x-axis and we pulled it, we stretched it. Let's clear this and put in the factored form. So what was it? It was x plus 7 by x minus 3. Graph it. Hopefully we see the same thing. That's good. Go to the table. Hopefully we see the same thing. And we do. Exact same values. The vertex, there it is. There's the peak. The lowest it goes is negative 25, and then it bounces back symmetrically on either side. Okay, so see green table. It's the same. Yeah? Okay. And then, just to verify this, we're going to go into y equals. We already graphed this one, and now along with it, I'm going to put in x squared plus 4x minus 21. Perfectly aligned. So the tables are perfectly aligned for equality, and the image is perfectly aligned for equality and being the same, or being treated the same. And here, so perhaps instead of creating this whole thing over again, we'll just say, see green, it's the same. Okay. And that also means maybe I can extend this. And maybe I can find that. So I'm going to spend a moment. I have a ruler from when we were doing the triangles. Ooh, look it. They do line up. This is cool. Sorry. Didn't do this on purpose, but I can keep creating my ticky marks, counting by ones, right? And notice that this would be what? 1, 2, 3, 4, 5, 6. It should have been here, I think. Because if we notice, this is 1, 2, 3, 4, 5 away. 1, 2, 3, 4. Should have been right there. So just our estimate was a little bit off, but that's okay. Okay. So now we see a new thing whereby it was still easier to graph this using the general form, because we could find the vertex, use our table of values, and plot the table. But another thing is surfacing. I see that this graph, the image of this graph of this parabola for this quadratic, meets the x-axis at 3, and I see a factor whereby if I put in 3, I get a 0 here. Also, on the other side, I see that when x equals -7, this factor turns into 0. And so there's something to be said about where it hits the x-axis and these factors. There's clearly a relationship here. The general form was easier for us to find the vertex and make a table. The factored form isn't as easy to find the vertex in the image, but it is telling us where it hits the x-axis. So things to note. All right, number 6 says to do another verification and then graph. Okay, let's verify. X plus 2 times the line x plus 2. So multiply this linear factor by this linear factor, and I'm noticing that they're the same. X by x is x squared. X by 2 is 2x's. 2 by x is 2x's. 2 by 2 is a 4. So we get x squared. 2x's in addition to another 2x's is in fact 4x's altogether. It's good to go. And then, okay, go through the motions. Vertex. Okay, wait. That's silly. X equals. And I go back to my general form and I see A equals 1, I see B equals 4, and I see C equals 4. And the vertex happens where x is equal to the opposite of 4 over double the A. It's happening at -2 again. Uh-oh. And I create a table of values. When x is -2, let's compute. -2 squared is 4. 4 plus 4 is 8, but 4 times -2 is -8. Wait a minute, 4 plus 4, is it 0? Wow. Okay, so I think our y values are going to be more positive this time. -2, 0 is at the center of our image. And so I'm going to go, there are some, those are actually above it, or to the right of it. Oh well. These are to the left of it. Normally I go from the left to the right. Oh well. So -1 squared is 1. 1 minus 4 is -3. -3 plus 4 is 1. If we plug in 0, that's the easiest thing. It's nice. 0 plus 4 zeros plus 4. Well, 4 zeros is 0 still, so this is 4. And this is going to be symmetric across the vertex. Okay, so I'm going to exploit that. And I'm going to use the fact that I picked mirror image equally distanced apart from the vertex values. I don't have to rescale. Yay! And plot. So what do we see? We have 0, 4. 1, 2, 3, 4. Got it. -1, 1. Done. -2, 0. Check. 3 to the left, 1 up. Got it. 4 to the left, 4 up. Oh, look. It's like a parabola that we didn't have to do very much scale thinking for. It's our friend. There's our friend. Okay, and now, because we verified this, see image on right. Yes? It's going to be the same graph, and let's verify. So now we've also learned that our calculator is a pretty good handy tool when it comes to making sure we're right. So what did we say? We said x plus 2 times x plus 2. We said that that was equal to x squared plus 4x's plus 4. And I'm going to actually go zoom. It's still thinking. Oh, that's good. It landed right on top of itself. Zoom, and I'm going to go to 6 standard. So there's the factored form image, and here is the general form image. Yay, same. And that verified that we actually graphed correctly, so that's nice. And I also want us to notice, so a few things happened. First, I still went to the general form in order to find the vertex and create the table of values. But then when it came to finding this x-intercept, notice right there, it happens at -2, and that is the number that makes both of these 0. So -2 is quite spectacular and is appearing in the factored form as opposed to the general form. So each of these has its perks. Let's write that down. So a couple of remarks.